Hello, and welcome to this new set of series of videos. Today I'll be covering a Couette viscometer and deriving a torque balance equation for it, demonstrating that the torque on the inner cylindrical surface is equal to the torque on the outer cylindrical surface. So let's go ahead and let's get started.
Alright, so I've gone ahead and put these different equations that were given up on the board as well as a visual representation of what the Couette viscometer looks like. So before we get started, let me give you a better picture of how it works and the concepts that we were covering. So we're given a Couette viscometer, which is used to determine the viscosity for a Newtonian fluid, which is this in blue. We don't know what it is, it doesn't matter right now, it just says water, not important to what we're solving for. And so there is a large cylindrical surface, and within this large cylindrical surface, there's an even smaller cylindrical surface, and in between these two, there's the Newtonian fluid that we're calculating the viscosity for. How this works is that there is a force or some rod being applied onto the smaller cylindrical surface that causes it to rotate and causes the liquid within it to get some speed that we have this equation for. And while the outside cylindrical surface remains doesn't move. And how this works in real life a little bit, give you an example. Let's say you have a say cup of water and you put it on the table. You simply want to spin the contents with your finger just by spinning it. As you can see, the liquid will start to splish around and start moving, and it will cause the cup to start moving. And we don't want this, as if the outside of the cup will start moving, or the outer cylindrical surface will start moving, we won't be able to find a said viscosity for the Newtonian fluid. So what we need here is to hold down the cup so that it doesn't stop, so that the outside of the cup does not move while we're spinning the inside components. So what we're going to need to do is we're going to need to put some sort of force upon this outer cylindrical surface to make sure that it does not move. Okay, so now we've got that covered. Let me talk to you a little bit about how this Couette viscometer looks like from a top-down view. So we have this bigger outer cylindrical surface, and then this smaller cylindrical surface, and in between we have this said liquid spinning at this angular moment, right? And we're given these different R values, right? So we know that this is our Ri, right? And this is our outer radius, right? Simple. Our inner radius for the smaller cylindrical surface, and the outer radius for the greater cylindrical surface. And what we're using here, we're assuming a no-slip boundary condition, which pretty much assumes that the velocity of a fluid against the surface is equal to the velocity of that surface, which simply meaning that the velocity of the Newtonian fluid up against the inner surface is going to be going at the same velocity as that cylindrical surface is moving at, and then same for these outside, but we know that this outside radius, or this outside cylindrical surface is not moving, so that we know that the momentum here would be equal to 0, right? So now we got that covered, we know we want to figure out what this is for, and as you can see, this little r that we're determining is for the r distance between the inner radius and the outer radius to find the momentum at any of those given r's. So now that we got that covered, let's go ahead and let's get a little bit started with this equation. So we have these two given equations for angular momentum with omega, k, r, and a bunch of values that you guys are probably confused. So let me explain. K, first of all, is simply just the relationship between the inner radius to the outer radius, r sub I over r, and then we can just simply plug that into this equation to work it out. But what we're solving here is to demonstrate that the torque and the force on this inner cylindrical surface is equal to the one to the outer cylindrical surface. So to do that, we pretty much only need these two equations and then another two equations, which we've seen a lot depending on torque and shear stress, and they both are with tau. So I'm going to be using tau for the torque equal to the perpendicular force multiplied by the radius, right? And then we also have for, like I said, shear stress, and I'm just simply going to write this as big S little s, and it's simply equal to the force divided by the area of said fluid, right? Then we can also rewrite that as simply equal to the viscosity multiplied by the shear stress, or by the viscosity multiplied by omega. Then from there, we can go ahead and get started, get solving for the torque on the inner radius and the outer radius. So now that we have these two equations, we can rewrite this equation of torque with the equation for shear stress. So with that, I'm going to rewrite this as torque is simply equal as, we're going to be taking force out, so we're just going to do shear stress times the area, and then still going to have the multiplied by the radius. And we can go ahead and rewrite this again by using this and using the viscosity and the shear rate. So we can rewrite the shear stress as viscosity times the shear rate multiplied by the area and radius. So there we have our new equation for torque, and now we can go ahead and solve this. Area is just an easier something to solve, so we can save that for later. Same with viscosity, we can empty that out later. So we're going to go ahead and start with the shear rate. So as we can see, shear rate is simply equal to the derivative. So let's go ahead and start working that out. So shear rate for the inner radius simply equal to inner radius multiplied by derivative of the angular momentum divided by the radius, right? So I'm going to go ahead and write that out, and I'm simply just going to divide this part by the radius, as this would be constant, so I would have divided by k squared, k squared multiplied by squared over r minus r, right? So, and then we have all this divided by r, right? So then from that, we can simply get the shear rate for the inner radius is simply equal to inner radius times the derivative with respect to r of omega times k squared, and this whole expression multiplied out, this divided by r, right? And we have r squared over small r squared minus 1. Now we want to find the derivative of this with respect to r. So let's go ahead and do that. The inner radius, we're going to have r1 out, and then we're just going to multiply it by the derivative. What we have here, we're just simply going to have, this is going to remain a constant, so I'm not going to touch that, and only going to derive this with respect to r. Negative 1 is just going to 0, and then just going to use this 1 or r sub negative 2. So then we're going to get negative 2 out of that derivative, so we have negative 2 w is k squared minus this constant, and then now we have x cubed over r squared. Right. And then now we can multiply r1 out. So now that we have this, we can go ahead and rewrite it with r1 equal to k squared over 1 minus k squared r squared over small r squared. And what this brings back, if you can remember this, big R over small r is simply the inverse of rk, right? So what I'm going to do is put the inverse of k into for this value, so that we have now shear rate is equal to k squared over 1 minus k squared. And then we have this multiplied by k over, or k to the power of -2, and then we can now multiply these out so that we can finally get that the shear rate for the inner radius is simply equal to this expression right here. This is for our inner radius equation, the shear rate, and then now we can go ahead and put that back in for tau to get us for, or plug it back into this equation to get us for our inner radius. I'm just gonna go bring this and write this back over here so that we have tau for our outer radius. So I'm just using this, bring it back over here and plug it in for our shear rate. So then we have viscosity, and now our inner radius, so we put that in over 1 minus k squared multiplied by the area. And like I said, this was easy. You can simply multiply it, and we know it's a cylindrical surface. So we know that the area is equal to 2 pi RH. So I have to write that 2 pi RH R1, and then for our radius, and then we're just using R1 again. Then just go ahead and simplify this out, right? Sorry, I wrote outer for some reason, a little bit of looking for the inner radius. So multiply this out, we can get -4 and R1 squared H, and then got everything, and all over 1 minus k squared, right? So I'm gonna rewrite this to make this a little bit better looking. Inner radius is equal for our initial height multiplied by 1 over 1 minus k squared. There we go. There is for our inner radius, or for our inner cylindrical surface, and now we have to go ahead and do that for our outer. So I'm gonna erase all of this stuff, make some room for our outer radius. So now the torque for the outer cylindrical surface, what do? We do the same thing that we did for the inner cylindrical surface. We start off with solving for the shear rate, right? So I'm going to go ahead and rewrite that same idea for the outer. I'm just going to go ahead and rewrite what we had before because it's the same derivative. So we're going to have square root of 1 minus k squared all over r squared over r squared minus 1. Right. This is what we have for the outer, so let's go ahead and solve that for the derivative. Now this out, and we're going to end up having is it's going to remain constant, the first half of the equation. Then for the right hand side, we're just simply going to have what we had earlier, r cubed, and then we write this again as, oh sorry, I almost messed that up. Totally forgot that we were doing it for the derivative. So we got to pull out the -2 out here, right? So that we have which is r and then -2 1 minus k squared big R over very similar like what we previously had, right? And again, we have this big R squared over the little r squared. So we're going to go write that for k, right? Bring that back down. We write the shear rate as over 1 over 1 minus k squared. As you guys can see, they're starting to look a lot like our inner. I apologize, the shear rate should not be the same as it was for the inner radius, as they're different surfaces, so I apologize for that, and rewrite this because we're not dealing with the inner radius now. This little r becomes our big R, right? Because the radius we're dealing with is the outside radius, which is the big R. So this is simply big R squared over big R squared, which is simply just 1, so this cancels out. So that now the shear rate is simply equal to that equation minus the R squared. So this is what we have for outer shear rate, and then we can go ahead and do what we did for our inner cylindrical surface and plug it in for into that equation. So I'm going to go ahead and bring this down here. We can see that this is our inner and this is going to be for our outer. Oops. So the equation we have viscosity times area times the radius, right? Okay, and then this R again, we're not using the inner, but we're using the outer radius. So then if you write this for the outer radius, again, viscosity times shear rate, which we wrote over here. Just put that over. K squared over 1 minus k squared. Alright, and for the area, same area that we're dealing with. 2 pi big R h. Right, and again, we're using the outer cylindrical surface. Then multiply by big R. Then we're going to go ahead and rewrite this down. For the outer, you can see that it's starting to look like a whole lot like that. Put this out, we got negative 4 pi viscosity. And we have the two R's, H. What are we missing? And then we have this k squared over 1 minus k squared. Right? Yep. Then we can go ahead and rewrite this. R squared, and bring this back to k. We know that a little bit of space, but big R, if you rearrange that, is equal to over k, right? So we can go ahead and square that out here, so that we get that it's equal to, this whole thing remains the same. 4 pi h. Simply rewrite r squared with ri over k. We write that as r sub I squared over k squared, and you multiply that with this k squared, so that we get simply r sub I squared multiplied by 1 over 1 minus k squared. As you can see, finally, we've achieved balance as the torque applied on the outer is equal to the one applied into the inner cylindrical surface. Hopefully this video has helped everyone, and have a great rest of your day.